Hi everyone, I'm Paritosh. I'm from EPFL. In this video, I'll be talking about robust algorithms under adversarial injections. This is joint work with Sagar, who's at University of Vienna, and Lars and Ola, who are at EPFL. Before I start my talk, let me just summarize what I'll say in my talk. So first, I'll present the motivation for our work and our model. Then I'll present our model, adversarial injections, and I'll cover some interesting and surprising facts about it, which would make it compelling to study. And lastly, we study submodular maximization in this model, which would lead us to interesting open questions and results. So I'll be covering a streaming algorithm in this talk. So let me just define it first. Also, let's assume that you have a problem about collecting Pokemons that you would like to solve. So you have the input stream where the elements appear one at a time, but your memory space is limited, so you cannot store all the elements you see. At the end of the stream, you have to output a solution. Now, this is a widely studied model in the literature. It was formalized in the seminal work of Elon, Matthias, and Szegedi. And streaming algorithms are very practical. They have several applications in fields like databases and networking. So what we saw in the previous slide was what happens after the stream is prepared. But there are several ways of preparing a stream, and people like to study this one that they call adversarial order. So adversary chooses the elements first. So let's say he chose these elements. Finally, adversary also chooses the arrival time of these elements. So in this model, the adversary is very powerful. That's why it leads to worst case guarantees, and this is not satisfactory. So for example, for the problem of streaming monotone submodular maximization, we know that we cannot beat half. So there is a lower bound that you cannot beat half. Also, for the problem of maximum matching in the streaming setting, beating half is a major open problem. To remedy these worst case guarantees, people like to study what they call the random order model. In this model, adversary chooses the elements first. But then the adversary doesn't choose the arrival time of these elements, but the arrival time is chosen uniformly at random between 0 and 1. Now, this obviously leads to good guarantees because the adversary is not as powerful, but the algorithms tend to overfit. For example, algorithms tend to bucket the stream, and then they assume that these buckets are representative of the whole stream. And therefore, even when the streams are perturbed very slightly, the algorithms do not work as they should. To prevent overfitting for problems for the secretary problem, Braddock and others very recently introduced what they call the Byzantine model. So other models have been introduced before in the literature, but we study this model because this is very much related to us. So in this model, there are two types of elements, noise elements and the good elements. Adversary chooses the elements and also their type. So let's say he chose this to be noise, noise, good, good. Then adversary chooses the arrival time of noise elements. And then the arrival time is chosen uniformly at random between 0 and 1 for the good elements. Finally, the quality of the solution is judged by comparing it to the best solution in the set of good elements. Well, this was introduced to remove overfitting with respect to algorithms for the secretary problem, but it still doesn't account for other kinds of overfitting. For example, algorithms for maximum matching and submodular maximization that worked in the random order model continue to work here. You can still divide the stream into two phases or bucket the stream so that the op elements are isolated. To prevent these kinds of overfitting, we introduce this new model that we call adversarial injections. In this model, just like the Byzantine model, adversary chooses the elements and their type. Just like the Byzantine model again, adversary chooses the arrival time of all noise elements. But here is the difference. Adversary gets to choose the timestamps for the set of good elements now. So let's say he chose 0.2 and 0.3. Finally, the good elements appear uniformly at random in these time slots. And finally, we judge the quality of the solution by comparing it to the best solution in good elements, just like in the Byzantine model. Also, adversary can inject the noise elements around the good elements as he wants. It's because adversary gets to choose the timestamps of the good elements. And hence, we also name this model adversarial injections. So there is a subtle yet crucial difference with the Byzantine model, and it is basically in the second step when the adversary gets to choose the timestamps for the set of good elements. This also makes the Byzantine model easier because the adversary in adversarial injections might as well have chosen the timestamps to be uniformly at random between 0 and 1. So the earlier algorithms for maximum matching and submodular maximization no longer work because the adversary is more powerful. It can simply populate the initial part of the stream with noise elements. Hence, we have to design robust algorithms now. Also, more excitingly, this may lead to the design of new algorithmic techniques. So let's see what we do in this model. So we study two benchmark problems in combinatorial optimization. First being the problem of maximum matching, and then monotone submodular maximization with subject to cardinality constraint. We consider these problems in the online and streaming settings. So let's see what we know about maximum matching. Well, we know that in the random order setting, for both streaming and online order, but for both streaming and online setting, we know that we can beat half. For the adversarial order, due to a very recent result of Kamlat and others, we know that we cannot beat half in the online setting. And in fact, it's a major open problem to beat half in the streaming setting for adversarial order. In this paper, we are able to beat half in adversarial injections for the streaming setting. What do you think the answer to this question is? Can you beat half? Well, yes. It's basically because adversarial injections is harder, which means that any algorithm that works in the model adversarial injections simply works in the Byzantine model, and it works with the same guarantee. So this is basically our observation that Guru Ganesh and Singla's algorithm, which works in the random order online setting, also extends to the Byzantine model online setting. Now, this is a tricky and an interesting question. Do you think you can beat half here? Well, it may be tempting to say yes, because we could beat half for the streaming setting in adversarial injections. So it's plausible that we could also beat half in the online setting. But the answer rather surprisingly turns out to be no. And this is basically our observation that the hardness construction of Kamlat and others basically extends to this model. So we know that the adversarial injections model is strictly harder than the Byzantine model. Also interestingly, in terms of beating half in the online setting, adversarial injections behaves as adversarial order, and in the streaming setting, adversarial injection behaves like the random order. So what do we know about submodular maximization? Well, in random order streams, we basically know that the right constant is 1 minus 1 by E. For adversarial order streams, we know that the right constant is half. So this creates an impression that we basically know everything, but not quite, because there's an interesting problem here. In our model, we are only able to prove a 0.55 approximation. So there's still a gap between 0.55 and 1 minus 1 by E, and we don't know what the right constant is. Also, the adversarial injections model is strictly easier than the adversarial order because we could beat half, and there is a lower bound of half in adversarial order streams. So let me just summarize what we know about these four models in this graph. We know that the random order model is the easiest, and this is what we would expect. The adversarial order model is the hardest. It is the worst case, and we simply hope that it doesn't happen. The Byzantine model is reality 1.0, and it lies somewhere between the adversarial order and the random order. The adversarial injections is reality 2.0, and it's harder than Byzantine model, but still easier than the adversarial order. Now we move to the main focus of this talk, which is submodular functions. So submodular functions are basically set functions from subsets of a ground set V to that of real numbers. They have a natural diminishing returns property, which means that for any two sets S and T, such that S is a subset of T and S and T are subsets of the ground set V, the increase in the function value that we get after adding element E to the set S is more as compared to T. F is defined to be monotone if for the two sets S and T that are subsets of V, the value of the larger set is more. Also, it's interesting to study submodular functions because they are fundamental objects of study in combinatorial optimization. Functions such as cut functions in graphs and set coverage functions are submodular functions. They can also be viewed as a discrete analog of concave functions due to their natural diminishing returns property. Also, due to this natural diminishing returns property, they are in fact very useful in several real-world tasks related to data summarization and machine learning. So let us now see an example of a submodular function. On the left of your slide, you can see a coverage function. The ground set for this coverage function is basically the set of rectangles, A, B, C, D. So what is the value of f of A? It's 2 because the green rectangle is covering 2 orange circles. F of AB is 5. And we can see that it's monotone over here because A is a subset of A comma B and its value is lower than the value of A comma B. Also, if you don't have any rectangles, then you don't cover any orange circles. That's why f of phi is 0, f of d is 1, f of ABC is 6, basically because we cover the entire space. f of ABCD is 6 again. Now we see an example of submodularity here. To see that, uh, uh, just see when like you added D to the empty set, you covered one orange circle, but when you added D to the set ABC, you did not cover any extra orange circle, and this is basically submodularity at play. So let's see what our problem is. So we are given a monotone submodular function f, and we have a stream sigma. At the end of the day, we have to output a set S of elements of cardinality at most k that maximizes f of S. And we would be compared against the optimum solution O in the stream. In this talk, I'll present a proof sketch of a 0.55 approximation algorithm that stores a number of elements that's purely a function of k. So the tree algorithm that I'll describe is best understood by seeing an example, and the algorithm itself is given in the top right yellow box. So we start with the root, which is the empty set. We insert the element A to the root with a value of 2 because it covers 2 orange circles. Then we insert B. For this example, the value of K is 2. So the height of the tree is at most 2. Also, for ease of presentation, I assume that the set of all possible increases in F is small. So the number of nodes in this tree is bounded. Now I add C. Now notice that I did not add C to the root because it provided me an increase of 2 and A was already present, which provided me an increase of 2. Now I add D. And finally, I output the best leaf, which in this case happens to be B, which has a value of 5. So I output the solution which contains the elements A and B. So let's see why the algorithm I described on the previous slide is a half approximation. So let's consider that this is the stream we have. I will define a solution sol, which I would prove to be a half approximation later. So let's consider the stream up to when the first opt element arrives. Now we pick the first element that provides the highest increase to sol. Let's say it is S1. By definition, f of S1 is at least f of O1, which happens to be 1. Now we repeat the same process on the stream between after the element S1 until OK for k minus 1 times to get the final solution sol of k elements. I claim that in the first step, we lose at most f of S1 union O1 from opt. Why is that? In the worst case, the new stream starts from A3, and therefore we lose O1 from the remaining set of opt elements. On the other hand, we also lose a value of f of S1 from opt, as it might be intersecting with the opt elements. So if the value of f of S1 was 1, we gained 1 in our solution, but we lost at most 2 from opt. Hence, applying this argument consecutive times, we would get that sol is a half approximation, but it's actually better if we pick opt element sometimes, and this is best seen by seeing the claim here. So we lose a value of f of S1, O1. And in this case, S1 happens to be O1. So we lose at most f of O1, and we also gain f of O1. So what if we never pick any opt elements? What can we say about sol? So formally, the ith element that is picked by a solution sol is defined to be the element appearing in the stream after Si minus 1 up to Oi, which provides us the maximum increase to our function f, given the fact that we have a partial solution of I minus 1 elements. So what can we say about Oi for any I, having picked a partial solution of I minus 1 elements? Well, notice that no matter what the input permutation of the opt elements, sol I minus 1 is always the same. This basically implies that OI is uniform over the set of opt elements. Using this fact, we can conclude with this inequality. And this inequality might look familiar because this reminds us of the 1 minus 1 by E approximation of the greedy offline algorithm. And indeed, this is a 1 minus 1 by E approximation if opt elements are never picked. We combine these two extremes naturally to get 0.55. But we believe that it is in fact a 1 minus 1 by E approximation in general. So why are we not able to prove a 1 minus 1 by E approximation? This is because the distribution of the opt element OI may not be uniform after we have picked a partial solution of I minus 1 elements. To see this, consider the first element picked by a solution sol, that is S1. Well, it may be an opt element sometimes and a non-opt element some other times, depending on the opt element that comes in the first opt slot. Due to this fact, having picked S1, the distribution of the opt element that arrives in the second opt slot is no longer uniform. And this leads to correlations which get only more nasty as the value of k increases, and we are unable to deal with these correlations. So we saw that sol was a half approximation on adversarial streams. If opt elements were picked, then sol was strictly better than half. But when no opt elements were picked, it was in fact a 1 minus 1 by E approximation. We combined these two extremes in a natural way to get a 0.55 approximation. But we weren't able to prove a 1 minus 1 by E approximation, as sol is difficult to analyze exactly due to these nasty correlations. To conclude, we introduced the adversarial injections model, and the motivation was to eliminate algorithms that overfit to the random order model, but simultaneously being easier than the worst case model. We studied maximum matching and monotone submodular maximization with respect to cardinality constraint in the online and streaming settings. We were able to obtain a 0.55 approximation algorithm for the latter problem. So all the open problems that we have are from the latter problem that we studied. First is whether there exists a 1 minus 1 by E approximation algorithm for this problem. Second is whether our algorithm is in fact a 1 minus 1 by E approximation. We believe so. The third is if you can come up with an algorithm that only stores polynomial in k number of elements, but beats half by a significant constant, or even better, gets 1 minus 1 by E. Thank you for watching my video.